The V FET, also known as the Static Induction Transistor, or simply the SIT, represents one of the most extraordinary chapters in the history of semiconductors. In the early 1970s, Japanese engineers created power transistors whose electrical behavior and sonic character came remarkably close to that of vacuum tube triodes. And yet, despite all of their advantages, this technology vanished within only a few years. But the story itself began much earlier. The fundamental principle behind the static induction transistor was developed by Junichi Nishizawa as early as 1950. He is often regarded as the father of the Japanese semiconductor industry. Nishizawa envisioned a semiconductor device that would not function as a simple switch like a MOSFET, and would not exhibit the exponential behavior of a bipolar transistor, but instead would allow smooth, continuous, triode-like control of current. In essence, he wanted to create a triode made of silicon. And remarkably, he succeeded. The operation of the SIT is defined by three fundamental physical properties. The first is its vertical, deep channel structure. Unlike the nanometer-scale channels found in modern MOSFETs, this channel can extend 50 to 100 micrometers into the silicon. This depth allows the SIT to handle both high current and high voltage, while maintaining continuous, fully analog control. The second key element is the PN-junction gate. The SIT does not rely on a gate oxide. Instead, the gate directly influences the conduction channel by controlling the density of charge carriers, in much the same way that the control grid regulates current flow in a vacuum tube triode. This direct interaction is one of the primary reasons for the SIT's distinctly triode-like behavior. The third defining feature is depletion-mode operation. An SIT conducts by default. With zero gate voltage, current flow is at its maximum. As negative gate voltage is applied, the current gradually decreases until the device eventually reaches pinch-off. This behavior is the exact opposite of a MOSFET, which is normally off and only begins to conduct once its threshold voltage is exceeded. Because of this, the characteristic curves of the SIT never flatten abruptly. There is no hard saturation boundary. Instead, the output curves rise smoothly upward, closely resembling those of a vacuum tube triode. In every meaningful sense, the SIT is a true silicon triode. The first major audio applications of this technology were realized by Sony, although NEC, Yamaha, and Hitachi also developed their own SIT devices. Sony's most advanced implementation was the complementary pair 2SK82 and 2SJ28, which found their way into several now legendary amplifiers. However, an important misconception needs to be addressed. The Sony TA-N88B was not a conventional analog SIT amplifier. It was, in fact, an early PWM-based digital power amplifier. In this design, the SIT devices were not operating in their triode-like linear region, but rather as switching elements, with an output LC filter reconstructing the analog signal. This does not diminish the engineering achievement. On the contrary, Sony was years ahead of what would later become modern Class D amplification. Still, the legendary sonic reputation of SIT devices was born in true analog operation. Distortion is dominated by second harmonic components. Clipping behavior is soft and gradual. Dynamic range is wide. And there is none of the harsh, mechanical character often associated with conventional transistor designs. This is why, even today, these amplifiers sound unlike anything else. And yet, the technology disappeared. Manufacturing SIT devices was extraordinarily complex, especially in the case of P-channel parts, where rejection rates proved to be extremely high. At the same time, MOSFETs were becoming cheaper, faster, and far easier to manufacture. The market itself was simply too small to support such an expensive and demanding technology. Put simply, the modern semiconductor industry was never built for this kind of device. That is why the V FET is not only rare, but fundamentally unrepeatably. So the question naturally arises, if the SIT was so good, why did it disappear completely? And why is it not manufactured today, when modern chips are produced with feature sizes measured in just a few nanometers? The answer lies not in a single reason, but in a convergence of multiple reinforcing factors. In the 1970s, the semiconductor industry evolved along two dominant paths: bipolar transistors and MOSFETs. The SIT belonged fully to neither. In structure, in operation, and in manufacturing technology, it represented an entirely different paradigm. One of its most defining features was the deep, vertical conduction channel, requiring thick, high-voltage epitaxial layers and extremely precise diffusion profiles. Tolerances were not measured in tens of percent, but often in 1 or 2%. Even on its own, this posed a severe challenge. The difficulty was compounded by the use of a PN-junction gate rather than a MOS oxide. While this direct gate interaction gave the SiT its unique triode-like character, it also made the manufacturing process extremely fragile. The true breaking point, however, came with P-channel SiT devices. Every manufacturer reported the same outcome. Producing them was a nightmare. Rejection rates frequently reached 60 to 90%. A minute deviation in the doping profile could render a device unstable or completely unusable. Entire wafer batches had to be discarded, and there were cases where not a single usable P-channel SiT pair could be produced from multiple wafers. Economically, this was impossible to sustain. Wafer utilization highlighted the disparity even further. A single MOSFET wafer could yield tens of thousands of usable devices. In contrast, a V FET wafer might produce only a few dozen N-channel parts, and at best a handful of usable P-channel devices. Manufacturers estimated that for every good SiT pair, 100 to 200 defective devices were produced. Even at the time, such costs were unacceptable. Many people ask today why SiT devices could not simply be manufactured again using modern nanometer-scale processes. The answer is that semiconductor manufacturing has evolved in precisely the opposite direction. Today's fabrication plants do not support deep, 100-micrometer diffusion, thick epitaxial layers, high-voltage PN-junction gate processes, or measurement systems optimized for linear analog operation. A modern chip factory is just as unsuitable for SiT production as it would be for manufacturing vacuum tubes. In the end, economic reality prevailed. Production costs exceeded selling prices, rejection rates were unmanageable, and MOSFET technology continued to advance rapidly. The high-end audio market was far too small to justify such an investment. Major manufacturers shifted focus: Sony toward digital technologies, NEC toward logic circuits and CPUs, Hitachi toward lateral MOSFETs, and Yamaha exited semiconductor manufacturing entirely. Within only a few years, all SiT production had ceased. That is why the V FET today is not merely rare, but irreplaceable. Its triode-like transfer characteristics, PN-junction gate operation, and deep vertical channel structure represented a technological direction to which modern industry cannot return. And that is why it can be said without exaggeration, the V FET is a once-in-history miracle of audio engineering, and the projects that attempt to preserve its character today are special precisely because they can never truly be repeated.